Welcome to lecture 22 of electromagnetic field and waves. Today we'll be talking about the incidence of electromagnetic waves on a conducting interface, and we'll also be extending our analysis of the skin depth, which we started last time. So as always, we'll start with a review of where we left off and what we covered last time in lecture 21. So last time we basically saw that if we have a conducting medium, then if your conducting medium has a conductivity sigma and J, which is the current density, we said is equal to sigma times the applied electric field, then under this assumption we can basically find that the charge density at any point as a function of time, the charge density rho of t can be given as rho of 0 times e to the power of minus sigma over epsilon times the time. Okay, we derived this last time, and we called tau to be equal to epsilon over sigma, and we called this the characteristic time, right, for 1 over e fall off. So if sigma is very large, then tau is very small. So as the conductivity of a metal conductor goes to infinity, tau goes to 0. So for a very good conductor, okay, we said that we can take the free charge density, okay, to be equal to 0. Okay, na? The free charge density to be equal to 0. I'll just write this a bit more clearly. So under this assumption, the Maxwell equations that we were working with were, firstly, del dot E was equal to 0. Secondly, as always, del dot B was equal to 0. Thirdly, del cross E was equal to minus partial B by partial T. And then the fourth and final differential equation that we were using was that this is Ampere's law. Del cross B was equal to mu epsilon partial E by partial T, as we always had, and then the term due to the current density, which was sigma mu times the electric field. So these were the Maxwell equations that we were working with, and then using these we basically found the wave equations, which for the electric field was that del squared E turned out to be equal to mu epsilon del 2E by del T squared plus mu sigma partial E by partial T, right? And we had a corresponding wave equation for B, which was that del square B was equal to mu epsilon del 2E by del T squared plus mu sigma times partial E by partial T. These were our wave equations in conductors. Now moving on, within these conductors, we basically saw what our plane wave solutions look like, and we saw that we saw plane wave solutions and basically that a plane wave solution of the form E of zt equal to some complex amplitude E naught e to the I of k tilde z minus omega t. We saw this satisfies the wave equation given that it can be expressed as following, as e to the minus kappa z e to the I of kz minus omega t, where k tilde is equal to some real part plus iota kappa, and that k tilde can, of course, if it's a complex number, it can be expressed as its magnitude a times e to the I phi, where phi was equal to tan inverse of kappa over k. And under this framework, then we can write the corresponding B field as k tilde over omega, which is the angular frequency, times E naught tilde in most generally, e to the minus kappa z e to the I of kz minus omega t. And of course, which we emphasized this last time, that since this kappa is now a complex number, so B has a relative phase with regards to E. So E and B are no longer in phase with one another in a conductor. And so this was basically capturing most of the physics that we discussed last time. Now today, like I said, so today we want to look at reflections from a conducting interface. And this is basically section 4.2 in chapter 9 of Griffiths. That'll be our primary source of discussion, but of course we'll add in with new ways of adding more detail for your understanding. So the basic geometry of our problem would be the following. So this, let's say, is your interface between medium 1 and medium 2. Now medium 1 is a dielectric and medium 2 is a conductor, and my axes would be as follows. The positive z direction would be going from medium 1 to medium 2. The x-axis would be along the parallel to the surface, and the y-axis would point out to the plane of the page. And so you can imagine that this is in fact a surface. It's the interface is of course a surface. It's not just a line, and so I'll just try to represent this surface like that. And what we'll have is we'll have electromagnetic waves that are incident and then they are transmitted through. Now, for this problem, as we always do, so we'll have some incoming wave vector and we'll have some transmitted wave vector and we'll have some reflected wave vector, and we'll try to find what these are. Just to give you a small hint, the transmitted wave vector, as you might expect, would be a complex wave vector because it's inside a conductor, and in a conductor we've seen that the wave vector is a complex entity. Now, as always, this is the third time that we're looking at interfaces. We first did it for normal incidence between two dielectrics. We then did oblique incidence between two dielectrics, and now we're doing normal incidence between a dielectric and a conductor. And this is the last thing that we'll do with regards to interfaces. So, as always, we need boundary conditions. We need to know how the electric field above and below and how the B field above and below behaves. So let's start with our Maxwell equations. Now, first of all, our first Maxwell boundary condition would come from the first Maxwell equation, which to start off is that del dot D is equal to the free charge density rho f. right? And so the integral over the volume of del dot D is equal to QF, the total free charge. Now if you make a Gaussian cube, if you were to make a Gaussian cube like that above and below, then on that cube what you will see is that the integral over the volume V of, so del dot D dV is equal to the surface integral, I'll just use a single bracket because I'm using a single bracket for the volume integral also, over the surface of D dot dA, which is just equal to surface charge density on the interface times the area. So if we simplify this a bit, and we've done this before, what we get is that, so I'll just draw a separating line. So D1 perpendicular to the surface, so parallel to the surface normal, dot A minus D2 A is equal to rho FA. What we get is that D1 perpendicular minus D2 perpendicular is equal to sigma F, and so epsilon 1 E1 perpendicular minus epsilon 2 E2 perpendicular is equal to rho F, right? And this is our first boundary condition. So this is condition 1. And just to be clear as to what we've done here, all we've done is that we've taken our interface, which was the interface between medium 1 and medium 2. Within that interface, we've basically drawn a Gaussian cube, something like that, above and below. And on that cube, we've basically calculated the surface integral, and so basically we've gotten contributions from the top and the bottom surface, and those are these contributions, and that's equal to sigma F times A. And so we recovered these boundary conditions. This is the first boundary condition we have. We've done this before. You can go back to your notes and check. This is nothing new. These are just the boundary conditions that we once derived quite a few lectures ago. Similarly, we can get our second boundary condition from the B field, which is just that B1 perpendicular minus B2 perpendicular is equal to 0, because once again, if you make a Gaussian surface, there is no magnetic charge, so the right hand side is 0, so you just get this condition. So our second condition is just that B1 perpendicular is equal to B2 perpendicular across the interface. I just put a box around this, and this is condition 2. And similarly, we get our third boundary condition, which is that E1 parallel is equal to E2 parallel. How do we get this? Well, you once again just take your interface, you calculate a loop integral like that, and you see how much area is enclosed in between them, and you can basically take the width of the loop to 0, and so the area goes to 0, and via Stokes theorem you just get that this is equal to 0. We've done this also before. And the let me just stick to our convention, make a box around this, call this condition 3. And so our fourth boundary condition basically becomes that B1 parallel minus B2 parallel over mu1 over mu2 is equal to Kf cross n hat. And what Kf is, if you remember, was the free surface current and what n hat was is the surface normal. Make sure you understand where these come from. If you need to revise, you can either go back to your notes or you can look at section 3.6 chapter 7 which is electrodynamics. Okay, in Griffiths. So either one. Make sure you understand these boundary conditions and where they're coming from. Now, if we agree on these, then we're actually in a better position of solving our problem. So once again, we will consider a monochromatic plane wave which is propagating along z, polarized along x, right? And so obviously it's incident normally at the interface, right? I mean, once I specified the direction of propagation and once I specified the polarization, it was pretty obvious that that it's incident normally, right? So we can write the so we can basically write the incident electromagnetic wave. We can express this as E incident as a function of zt is equal to E incident. I'll put a tilde so that because this can be complex, e to the I of k incident z minus omega t x hat, b incident of zt is equal to in terms of E, it's just ei over v1, which is the velocity in v1, e to the I of ki z minus omega t. The direction is the y-axis because it's k cross x. So if you do z cross x, it points in the positive y direction. So it's y hat. So that's your incident electromagnetic wave. Similarly, the reflected electromagnetic wave is given as, so EI of ZT is given as E reflected tilde, because it can be complex, e to the I of minus k 1 z minus omega t, also polarized along x. I've put a minus sign here, so I can just put the same wave vector here, which was the incident wave vector, and the reflected B field would be E reflected over V1 e to the I of minus k I z minus omega t y hat, but there will be a minus sign here which just comes from Maxwell equations, right? Why? Because E cross B has to point in the direction of propagation, right? So something has to be different between this and this, and you can check that. We also had this when we looked at normal incidence at a dielectric interface, and the transmitted wave EM wave is given as, now this is where it gets really interesting, or somewhat interesting. E transmitted of zt is equal to E transmitted tilde e to the I of k tilde z minus omega t x hat. Notice that this propagation vector, this second propagation vector, is now has it has a tilde on top of it, right? Because it's inside the conductor now. And similarly, B transmitted zt becomes equal to k tilde over omega, let's say k2 tilde over omega, e to the I of k tilde to z minus omega t, and it points in the y hat direction. So these are in the conductor and these are in the dielectric. And make sure you understand everything basically on this slide. And now let's say that our interface occurs at z is equal to 0. Okay, so our interface occurs at z is equal to 0. So this is our interface. This is our z-axis, this is our x-axis, this is our y-axis, and we have some incoming k incident, we have some reflected k reflected, and we have some transmitted k tilde, right? And we want to find the corresponding magnitudes of the electric and magnetic fields. So let's get started. Now, this is n hat, right? N hat points in the negative z direction, which is the surface normal. Now, let's apply our boundary conditions. Now, our first boundary condition, condition 1, basically tells us that epsilon 1 E1 perpendicular minus epsilon 2 E2 perpendicular is equal to any surface charge density over there. But notice that there is no component of the electric field perpendicular to the surface, right? The electric field points on the x-axis, and that's completely parallel to the surface. So E1 or E incident perpendicular is equal to 0. So as a result, E1 incident perpendicular is equal to E2 epsilon 2 E2 perpendicular, and all of this is 0, right? So the first boundary condition just reduces to 0 basically. This also implies that sigma f is equal to 0. Surface charge density is also 0, right? Because there's no component of the electric field which is perpendicular to the surface. Now let's apply condition 2. Now condition 2 basically tells us that B1 perpendicular is equal to B2 perpendicular, but B1 perpendicular is also 0 because there's no transmitted there's no incident or reflected magnetic field which is perpendicular to the surface. It all points in the y-axis, and the y-axis is parallel to the surface, right? Not in the z direction. So then B1 perpendicular is also 0, which is equal to B2 perpendicular. So the second boundary condition also doesn't really give us much. Okay. Now let's look at condition 3. Let's look at boundary condition 3. Now boundary condition 3 tells us that E1 parallel is equal to E2 parallel. Now we're actually getting somewhere. So what this allows us to write, what's the total electric field in medium 1? So this is medium 1, and this is medium 2. So we can basically express this as E incident tilde plus E reflected tilde is equal to E transmitted tilde. Okay, and we will call this equation 1 because boundary condition 3 has finally given us one equation that will be useful to us. Okay, now let's apply condition 4. And this is where it gets quite conceptual. So condition 4 basically tells us that B1 parallel over mu1 minus B2 parallel over mu2 is equal to Kf cross n hat, where Kf is the free surface current. Now here's the thing. Last time we talked about skin depth, and we saw that EM waves decay in conductors. So any electric field in a conductor would induce a current. So you'll have a current J, which is equal to sigma times E. Sigma is the conductivity, and this would be a volume current density, right? And if you remember last time, we basically saw that the that for any conductor which has a non-infinite conductivity, you have some finite skin depth, and we'll explore this more at the end of this lecture also. So for any finite conductivity, E leads to a current density. For infinite conductivity, E can lead to K, where K is surface current. So if sigma is equal to infinity, then you can have then you can have K. If sigma is greater than 0 but not equal to infinity, then you can have J, but you can't have both. That's one way of looking at it. So another way of thinking about it is that if you have you see, because this is a surface current, K is a surface current. The way to think about K is that if you have some surface, for example, if you have some surface it's like that. K is this surface current K. Whereas what J is that if you have some sort of a pipe, then J is basically the total current over the area. So in some sense, the way to get K from J is basically to perform an integration. So if your J is finite, then since K is only one slice of a finite thing, it's actually zero for a finite conductor. And it's basically delta function, and so it gives you a zero. And so the free current K free is equal to zero for the case where you don't have infinite conductivity and your skin depth is not a delta function, and your skin depth is actually a finite number. So as long as your skin depth is a finite number, you have a current density, and the way to get the surface current K is equivalent to the integral of J from 0 to infinity in depth of the conductor for the finite conductivity case. Because you have to understand that what K is a surface current which is confined to an infinitesimally thin fragment of the interface. So that's why Kf is 0 for a finite conductor. I hope this is clear. If it's not, then we can discuss it further. Now, moving on, we can express our boundary condition as follows. So B1 parallel now is equal to B2 parallel. So B1 is the sum of the incident and reflected magnetic fields in medium 1. So that's B1 parallel, B incident parallel over mu1 plus B reflected parallel over mu2, over mu1, and this is equal to B transmitted parallel over mu2. But we know how to write the B field in terms of the E field. So E incident parallel over mu1 V1 minus E reflected over mu1 V1 is equal to now this is equal to K2 tilde over omega mu2 E transmitted. And so this simplifies as E incident minus E reflected is equal to K2 tilde times V1 mu1 over omega mu2 E transmitted. So if you define beta to be equal to K2 tilde mu1 V1 over omega mu2, so in that scenario then EI minus ER becomes equal to beta times ET, and we will call this equation 2. So this is one condition, and the other condition we derived was that EI plus ER was equal to ET. This was equation 1. So now we have our both equations, and using these we can find the transmitted and the reflected coefficients. So let's try and do that now. So adding equation 1 and equation 2, we get that 2EI is equal to 1 plus beta times E transmitted. So the transmitted electromagnetic wave is equal to 2 over 1 plus beta times the incident amplitude. Okay, this is our first equation, and substituting for EI, substituting EI into equation 2, what we basically get is that EI plus ER becomes equal to 1 over beta times EI minus ER. You can check this. So then beta ER plus ER becomes equal to EI minus beta EI. So ER becomes equal to 1 minus beta over 1 plus beta whole into E sub I, right? And this is our second equation. So now we have an equation for EI and we have an equation for EI. Now remember that, so beta is proportional to V1 mu1, the wave vector, over omega mu2. And you notice that this is very similar to the equations we had for the case of normal incidence on a dielectric interface. The equations are nearly identical. The only difference now is that beta is actually a complex number. Beta is a complex number. And so this is how these equations are different from the equations we had on a dielectric interface. And let's see the repercussions of this. So recall that K tilde is equal to K plus iota kappa. So K, for simplicity, let's just write. So K, if you remember, was equal to mu, sorry, K square actually was equal to mu epsilon omega squared over 2 into 1 plus sigma over epsilon omega squared, square root of this quantity, plus 1. Now, and of course we had kappa also, but we'll come to that afterwards. But this is enough. Now, for a perfect conductor, for a perfect conductor, sigma goes to infinity. So for a perfect conductor then, if sigma goes to infinity, then K goes to infinity. So if K goes to infinity, then beta tilde also goes to infinity, right? But if beta tilde goes to infinity, then that means two things. That means that E transmitted goes to 0 and that also means that E reflected goes to negative E incident. This is very interesting, because what this implies is that a conductor, an ideal conductor, reflects all electromagnetic radiation. And it doesn't just reflect it, it reflects it with a 180 degrees phase difference. And so in a perfect conductor there is no transmission. In an imperfect conductor there is some transmission, but still most of the electromagnetic radiation is reflected. And so this is why metals are shiny. Basically this is why. And this is why when you have a metal, let's say when you have aluminium, it's really shiny initially, and then gradually it begins to fade. And the reason it begins to fade is that the aluminium starts to oxidize, and the material at the surface is actually aluminium oxide, and aluminium oxide has a low sigma. So when you have a low sigma, then you have a low K, and so when you have a low K, then you have a significant amount of transmitted and scattered light, and so the reflectivity goes down because beta decreases. So that's how the chemistry and the physics come together into something that we see microscopically. And so basically when you have to make a mirror, what people basically do is that they take a glass substrate and they paint, they coat a metallic coating at the back, and you only need a very thin coating because of what we'll see now actually in the next section, which is the more concrete discussion of the skin depth. But yeah, you only need a very thin layer of conductor to actually reflect quite a lot of light, and so that's basically how mirrors are made. Moving on then, like I promised, I want to have a detailed discussion of the skin depth. Now, the whole argument behind the skin depth came from the fact that we saw that plane waves were basically given as E naught tilde, let's say with some polarization dependence, e to the minus kappa z, e to the I of kz minus omega t. So we saw last time that kappa squared was equal to mu epsilon omega squared over 2 into 1 plus sigma over epsilon omega squared. We take the square root of this and then we subtract 1. And this was basically the relation for kappa square, and compare this to the relation for k square before, and you'll remember. Now we define the skin depth using a simple delta. Well, from now on we'll use delta, and this is equal to 1 over kappa, because this is because when z is equal to 1 over kappa, the electric field falls off as 1 over E. Now what we'll do is that we'll take two asymptotic cases. So we will take the first case we will take, so case 1 would be when sigma, which is the conductivity, is much greater than epsilon omega, and case 2 would be where sigma would be less than epsilon omega, and we'll see what happens to skin depth in either case. So we'll see what happens to the skin depth in either case. Now let's take the first case. So case 1, where sigma is much greater than epsilon omega. Omega is the frequency of the wave. Now in this scenario, k square becomes equal to mu epsilon omega squared over 2 times sigma over epsilon omega. So this simplifies to mu sigma omega over 2, right? So K becomes equal to, so kappa becomes equal to mu sigma omega over 2, its square root. So the skin depth becomes equal to 1 over kappa, so that becomes equal to 2 over mu sigma omega and its square root. So this is the skin depth for a good conductor, right? And for frequencies where sigma is much greater than the product of the frequency times the permittivity. Okay. Now think about this a bit. I mean, for visible light, omega is of the order of 10 power 15. And epsilon is of the order of 10 power minus 11. So you would want sigma to be of the order of 10 to the power of 4. Okay. Anyways, now let's go to case 2. So in case 2, what we want is sigma to be less than epsilon omega. Now the way to do this would be to Taylor expand 1 plus sigma over epsilon omega square, the square root. So we have that sigma is much less than epsilon omega, so this thing is less than 1. So we'll do a Taylor expansion, and what that will give us is that so kappa squared becomes equal to mu epsilon omega squared over 2 whole into, so we're Taylor expanding 1 plus sigma over epsilon omega whole square, so that's 1 plus nx, so it'll be 1 plus 1 over 2 times sigma over epsilon omega whole squared minus 1, so on and so forth, and we just ignore the other terms. We just keep it to first order. So this is the Taylor expansion first order. Now under this approximation, then kappa squared becomes equal to mu epsilon omega squared over 2 multiplied by 1 over 2 times sigma over epsilon omega whole squared. So this simplifies to mu sigma squared over 4 times epsilon. So kappa is mu sigma squared over 4 epsilon square root. So the skin depth becomes equal to 4 epsilon over mu sigma square, and of course there's a square root over here, right? So this is the expression for the skin depth for poor conductors when the conductivity is less than epsilon omega. Now notice that if you have a poor conductor, then this is essentially what your skin depth becomes equal to, and sigma is probably a small number, so your skin depth is actually quite large, and it doesn't really depend on frequency. But what's very interesting is the expression for good conductivity, and if I just write it down again, we got that delta was equal to 2 over mu sigma omega square root for a good conductor. And this is where all the magic happens, because I mean, so you will study in condensed matter physics that conductivity is actually a function of the frequency for most materials. Actually, for all conductors. But you don't need to worry about that in this course. In this course, let's just imagine that the conductivity more or less stays the same for all frequencies. So let's say that for us, sigma is more or less constant till megahertz frequencies, and only changes slightly above it. Okay, so now why would conductivity depend on frequency? Well, you can imagine that in order for a material to respond the incoming electromagnetic wave, its electrons need to basically create currents at those frequencies, and the ability of the electrons of a metal to create currents at frequencies depends on the conductivity. But the conductivity, of course, depends on like the scattering time, or the current density, or the mobility of electrons within that material. So it's a material thing, and it's a topic for condensed matter physics. So for this course, you can imagine that it's more or less constant optical frequencies, which is of the order of nearly 10 to the power of so it's 10 by 8 over 10 to the power of, say, about 10 by 15 hertz. Anyways, so so most metals are good conductors up to very high frequencies, and let's see what the skin depth is for different frequencies. So at about f is equal to 50 hertz, so if you have an electromagnetic plane wave of frequency 50 hertz, so omega would be 2 pi, would be 100 pi. So the skin depth is approximately 1 centimeter. Similarly, at about f is, let's say, 50 megahertz, so it's a million times faster frequency. The skin depth delta is approximately 10 micrometers, right? Why? Because the smaller the omega, for the same conductivity, the larger the skin depth, right? And at the same time, at about f is, let's say, 10 to the power of 15 hertz, which is optical frequencies, skin depth is usually around of the order of 10 or 5 nanometers. So you can see that that the larger the frequency, for the same conductivity, the smaller the skin depth. Of course, you'll notice that I haven't really created a linear relationship. That's because the conductivity also tends to decrease at some point as you raise the frequency. But I mean, you can look at the Drude model, but that's outside the scope of this course. So you can just take my word for it. But this is a very good rule of thumb, okay? And this expression is very useful, and it works for a good conductor. So, so if you have a 10 nanometer thick coating of a metal, then basically you can block all visible light. But that coating will not block radio frequencies, and it will not block microwaves, and it will not block basically your line's electromagnetic wave, right? So it's because of this fact. So because of the skin depth, the following things happen. I'll just give you some examples. So because of skin depth, a can of Coca-Cola is impermeable to visible light. So what you have is a thin coating of aluminium or tin. I'm not entirely sure what metal it is. It's one of the two, or an alloy. So because of a thin coating of that alloy, the skin the thickness of that coating is much greater than the skin depth of optical frequencies. Hence the light attenuates, and so you don't get any significant transmission. Similarly, this is also why Wi-Fi signals get attenuated in buildings, right? Because of all the metal you use in the roofing systems, in construction, or that mesh of steel that you lay down. Well, that steel basically acts as a material that electromagnetic waves have to pass through, and so because of the skin depth, they die out. This is also why we have metal casings to shield sensitive electronics. Right, this is why you have most processors or sensitive electronics inside a metal casing, because your metal casing in your CPU basically prevents radio waves of a nearby tower, or your 60 hertz hum from basically getting into, or basically attenuates it a bit, and so that it doesn't couple to your circuitry a lot. So it has an effect over there. I mean, this is also why, this is very interesting, why so there's something called the skin effect. Skin effect, which is that power transmission lines, so carry most of the fields within 1 centimeter of the surface of the line. So if you have a very thick, so if you have, let's say this is the power line and it's very thick, then most of the electromagnetic waves are basically they're confined to this region. So there's no point in making a very thick power transmission lines because of the skin effect, because electromagnetic waves decay inside, so all the energy is carried. I mean, if we I mean, our main voltage is if the frequency is 50 hertz or 60 hertz, then that corresponds to 1 centimeter of skin depth. So in any power transmission lines, most of the energy is being carried in the first 1 centimeter, right? And this is also why and so for example, if you're doing very high frequency circuits, then in high frequency transmission lines, the electromagnetic waves are confined to an area even smaller than the 1 centimeter inside the transmission line. So you actually have resistive effects, and so that's why you have multiple thin wires that people twist together so that you have low resistance, right? And so this is also why microwaves have shielding on them. So anytime you see a microwave, there's always like this metallic mesh at the front, because microwaves are relatively low frequency waves. So a conducting mesh at the front basically decays most of the microwaves. I mean, in popular science, you must have seen conspiracy theorists wearing tinfoil hats. Well, this is why they wear tinfoil hats, so that aliens can't read their mind. I mean, it's all. I mean, of course, it's not real, but this is the physics behind it, basically. Um, and basically, one last thing that I want to talk about is that you might then think or ask that then why do X-rays? I mean, why is it so difficult to attenuate X-rays? I mean, X-rays are a very high frequency. The skin depth for them should be negligible. And so for gamma rays, my answer to that is that the frequency of X-rays and gamma rays is so high that conductivity is not the same, and so the skin depth isn't what it is for optical frequencies or lower frequencies. So at that point, conductivity starts playing a big role. This is basically all I wanted to talk about in with regards to specifically electrodynamics, the theory of it. So we've basically covered all Maxwell equations. We've covered dielectric interfaces. We've covered dielectric interfaces with oblique incidence. We've covered the Poynting vector. We've covered how electromagnetic waves and how electric fields behave in conductors. Um, we've covered the root of magnetism, for example, in terms of bound currents. We've understood bound charges for polarization. Now, in the next 4 or 5 lectures, what I want to do is I want to focus on transmission lines and practical transmission lines model and how we can transfer what we've learned here into those kind of systems. I hope everything is clear. If we can answer any of the further questions in our Q&A sessions on Zoom. Thank you very much for listening, and hopefully we'll have an assignment on this later this week. Thank you.